Good morning, everyone. I hope you enjoying the school. Yeah, it's not easy, and I'm afraid my talk also won't be very easy, but I'll try to keep it as simple as possible. So today I'll be talking about topological multi-K magnetic structures. I would like to take this opportunity to put this subject, this multi-K structures in more general context, my talk, in order to give you an idea not only about topology, about multi-K magnetic structures in general, and to give you some clue, some tools, if you want, in order to know how to approach these magnetic structures and how to distinguish them from a 1K structure, because experimentally it's not trivial at all to distinguish one and multi-K structures, but microscopically they're very different. And it's very important for physical properties to understand what kind of structure you are dealing with. Okay, here is a short outline of my talk, and we will start from a simple concept of topological defects, first from domain walls in one-dimensional ferromagnets, and we will consider more complicated cases of two-dimensional defects in two-dimensional ferromagnets, which are called skyrmions. And then we discuss the cases of ordered topological defects when they are ordered into three-dimensional lattices, so-called three-dimensional skyrmion lattices. And then we will discuss the way how we can describe this magnetic structure using crystallographic method. So in particular, we will figure out that these structures are actually multi-K structures. And we will discuss what kind of consequences of the multi-K nature we can exploit in order to understand actually in the general context of multi-K structures, in the context of coupling to secondary order parameters, and that will give us some idea how we can distinguish them from 1K structures. And finally, this will be a bit complicated part of my lecture, and then at the end I will show you some example how all these ideas work, and hopefully after that you will understand that actually is nothing complex here. Okay, so generally speaking about topology deals with spatial properties of objects which are preserved under continuous deformation. So on this slide you can see, on the left side of the slide, you can see two objects, it's a sphere and a wine glass, which looks very different, but from a topological point of view, they're identical. And same on the right side of the slide, you have a torus and a teacup, which are also topologically identical objects, and they can be transformed one to another. Animation doesn't work. Perhaps you have seen that. So they can be transformed one to another with continuous deformation. But objects from the left and from the right, like sphere and torus, for instance, they're topologically different, because torus has a hole while sphere doesn't. And whatever you do with sphere, with any continuous deformation, you cannot create a hole in this object unless you destroy this object, make a cut, or so you apply some energy. So you need to spend, the main message of this slide is that you need to spend, it costs energy in order to break topology. And let's see how the simple ideas work in magnetism. They actually work beautifully, and they can explain stability of some objects. And the simplest topological object is a domain wall in a one-dimensional ferromagnet. So if you take a chain of atoms and we attach a magnetic moment to each of them, and we assume that these magnetic moments have a easy plane type of anisotropy, so they can take any position in the plane perpendicular to the one-dimensional chain. So if we introduce this, what is called 2-pi domain wall, it's simply twisting of spins, and that is a topological object. Why it's topological? Because using a continuous deformation, we cannot turn it back into ferromagnetic state. So if we start doing that, we will inevitably go through the state where some spins point opposite to each other, so anti-ferromagnetic state. But that costs energy because our exchange interaction is ferromagnetic. So we cannot get rid of this object, with a continuous deformation. And that's why it's topologically protected. So we can also deviate spins from the plane towards direction of the chain. It's called escape to third dimension. But it's again, if the plane is easy plane anisotropy, it costs energy. So whatever we do in order to get rid of, destroy this object, we need to overcome some energy barrier. So the situation is very similar to the rope, where we have a knot on the rope. So whatever we do, when it's created, we can move it in towards or backwards, but we cannot get rid of that unless we unless we cut our rope, and then we can undo it. Okay, so using ideas of stereographic projection, it's very similar how we project our Earth, and it's a three-dimensional. It's a sphere, three-dimensional object into something flat. Using this same method, we can project our one-dimensional topological object into a circle. So why do we need this projection? Because like that we can easily quantify our topological properties. So you see, if we move from one side of our circle to another, our magnetization changes on angle d theta, for instance. And if we introduce what is called topological charge, so if you just sum together these angles when we go around the circle, in a continuous limit, it will be integral. This integral will tell us what happens with magnetization, what it does. So it's like in given case, in the present case, magnetization wraps around the circle. When we go around the circle, magnetization wraps around as well. So it's giving us a topological charge 1. So integer number, it means that this object is indeed topological. And the idea of topological charge allows us basically to distinguish topologically distinct objects or vector fields, if you want, in a continuous limit. Because in most cases, practical cases, I'll show you later, this continuous limit is well justified, because in real systems, magnetization changes very slowly in comparison with unit cell lattice of our discrete lattice, which is characteristic of the systems. So this slide demonstrates you several vector fields and the topological charge. So on the left we can see what is called topologically trivial, it's ferromagnetic state simply, with a topological charge 0, while at the middle you can see two vector fields with topological charge 1, and on the right with topological charge 2. So these two at the middle, they have identical topological charge. That's why they can be transformed continuously one to another. But these fields cannot be transformed to ferromagnetic state with a continuous deformation, because they have distinct topological charge. That implies that they topologically they're distinct objects. And below you can see with these lines what magnetization does when we go. So it wraps once for these two objects, for these fields, and it wraps twice for this one. Okay? So now if we go to a bit more complicated case of two-dimensional ferromagnet, we still can define our topological defect. It's called skyrmion. So it looks like this vortex type object. And if we cut this object with a plane, if you do 1D cut with a plane which is perpendicular to the plane of our physical space where our spins live, so we'll have exactly same, it will look exactly same as a 2-pi domain wall. So basically, this object can be created from this 2π domain wall if we take it and rotate it about the axis perpendicular to this one-dimensional object. Then we will recreate this two-dimensional topological skyrmion. And the fact that it's indeed topological object, so we can do exactly the same thing. We can take our stereographic projection and project this two-dimensional flat plane into a sphere. And like that, we can define our topological charge. But in this case, we are dealing with, so M is simply a unit vector along the magnetization on each point of a sphere. So we are dealing with a solid angle instead of simply angle in a plane, like in the previous case. So define it like that, topological charge tells us that indeed our skyrmions are topological objects because so it shows how many times magnetization wraps around a sphere in this case. And for skyrmions, this charge is integer number 1, while for ferromagnetic state it's again 0, telling that these two states are topologically distinct. And what is remarkable, about these objects that these skyrmion objects, they were predicted theoretically many years ago. It was 1988 by two Soviet physicists, Bogdanov and Yablonsky. So they were solving some Ginzburg-Landau functional for non-center symmetric crystal, and they found solutions which correspond to this vortex-type lattices, which are kind of analogs of abricos of vortices in superconductors. So skyrmions are not the only two-dimensional topological objects. There are plenty of other ones, anti-skyrmions, merons, with topological charge half. Anti-skyrmions are a bit like skyrmions, but to quantify skyrmions, you can also introduce some other quantities like helicity, verticity, and so on. So they will be different in this in helicity and verticity, but main idea will be same. And the talk is not about skyrmions, so I don't want to stay long on that, but there are just plenty of them. These objects are Hedgehogs object. It's three-dimensional topological defects. They look in a real space very similar how skyrmions projected into a sphere. So all this very nice, they're very beautiful, this object, but the real excitement to the field came in 2009 when a group from Munich discovered experimentally the skyrmion lattice in manganese silicide. So this material is a non-center symmetric cubic ferromagnet. So it's non-center symmetric, so exactly like in the theoretical work by Bogdanov and Yablonsky. And the ground state in zero field, ground state of these materials is a long period helical structure imposed by this non-center symmetric nature of the crystal structure, because non-center symmetric means that Dzoloshinsky-Maria antisymmetric exchange is active there, and competition between antisymmetric and symmetric exchange imposes this long period helices. So it's really long period modulation, and that's what justify, for instance, that continuous limit. For instance, when we are talking about these objects, we can use continuous limit. So the phase diagram of this material contains a so-called A phase. It's a phase in a narrow temperature and a field range, close to paramagnetic transition, where people believed for a long time that it's just conical phase. But when this German researchers had a look at that with neutron scattering. They found a confirmation that it's actually skyrmion lattice. So skyrmions are ordered into three-dimensional lattice in these materials in this phase. So it's two-dimensional objects, they create two-dimensional lattice, and then along the third dimension they propagate just like that without any changes, creating what is called skyrmion tubes. So discovery has been done using neutron, small angle neutron scattering. So they observed that 6 spot. Perhaps I'll back later and explain why it is an evidence of the skyrmion lattice. And after the discovery, so many experimental and theoretical works, of course, appeared. And apart from the classical mechanism, what stabilizes this skyrmion phase, which is antisymmetric exchange, Deloshinsky-Marie exchange, as was originally proposed by Bogdanov and Yablonsky. It has been shown that actually this ground state, this exotic ground state, can also be stable in centrosymmetric crystals as well, and the work by Maxim Mostavoy and Leonov showed that in the case of frustrated magnetic interactions and a right value of single ion anisotropy can also stabilize these objects in this ground state in centrosymmetric crystals. And if you look at the list of skyrmion host materials, which is quite long, this list, yes, it's dominated by non-centrosymmetric crystals. But there are few examples indeed, few examples with centrosymmetric crystals here actually shown in red. Apart from the bulk crystals, which shows this skyrmion lattice, there is a very long list of low-dimensional objects, structures, where skyrmion lattice is also stable. In thin films, heterostructures, and it's very natural because in these objects, the crystal symmetry at the surface is where lattices terminate is broken, and that imposes very strong antisymmetric exchange interactions, and that's what stabilizes this funny ground state, this skyrmion lattice. So why people are excited about them? First, of course, they're very nice, right? They look nice, these objects, they're beautiful, I would say. But apart from that, they also demonstrate some interesting physical properties and some useful. So some of them is, for instance, topological Hall effect. So ordinary Hall effect, I guess you know what is that. You just, when you put a conductor in a magnetic field, and you can read the voltage in the direction perpendicular to the current and magnetic field. And this ordinary Hall effect is proportional to the field. There is also anomalous Hall effect, which is observed in materials with spontaneous ferromagnetic component. And usually as a function of field, it follows this the follows also field dependence of magnetization, so ferromagnetic component, so it shows hysteresis. And on top of that, if we have a skyrmion lattice, we will have another contribution to a Hall effect, which is called topological Hall effect, which looks like that. It comes from the fact when conducting electrons interact with underlying skyrmion lattice, they rotate in real space, and this rotation adds some phase in the electronic wave function, which is called Berry phase, and this is kind of equivalent to existence of fictitious magnetic field, which deflect these electrons and give rises to this anomalous Hall effect. This effect can be huge. It's really huge, as has been recently demonstrated for this gadolinium to palladium silica 3 crystals. That is, by the way, examples of centrosymmetric skyrmion host material. And another, but what I want to say that point out your attention that actually talking about a topological Hall effect, that not only skyrmion latches, our materials with hosting skyrmion latches can show them. That's a little bit more general phenomenon. And in theory, any magnetic structure, what is called with non-trivial spin topology or texture, can demonstrate this effect. So what does mean non-trivial? It means that we can define some quantity, which is called spin chirality. It's a three-spin quantity, so it's just a mixed product between three spins. So if three spins are non-coplanar, and if this it's kept like that, if you take all three spins units, let's say triangular-based exchange topology, and go through the crystal, so they all show same chirality. So it doesn't average to zero, so it's macroscopically non-zero. Then we should also expect this topological Hall effect on this on the materials with this magnetic ground state. So it obviously that scalar chirality will be non-zero in skyrmion crystal, but it also can be non-zero in some other spin textures, or it can come from defects from domain walls, for instance, as well. So it's quite a lot of it. A list of materials which demonstrate topological Hall effect is quite long. And another cool effect is a reversed effect, basically, to topological Hall effect, skyrmion Hall effect. Because when conducting electron is deflected, it also applies some field, some force on skyrmion itself. And skyrmion can exist as an isolated object, you know, as an excitation. And that implies that you can move it with electric current, which is quite cool. Okay, so we are crystallographers, basically, and what is interesting for us is to consider how these skyrmion lattices can be described using our language, if you want, our tools. And the tool, from the symmetry point of view, you know, as Manuel just mentioned, that any type of magnetic order is a symmetry breaking process, and symmetry breaking process is usually described by Landau theory of phase transition. So I just would like to give you some very brief introduction to the Landau theory, but I think we can do it after break, right? Because it's time to make, it's 10 o'clock. Do you want to make a break, or shall I? Let's do a tea break and continue after the break.
Okay. The time was...
The lecture is not over, so you can, I mean, you can ask me questions after.
Have a question?
You can ask me after when I'll do the second part.
Can chiral domain wall be probed by neutron scattering?
Hmm?
How can chiral domain wall be probed by neutron scattering?
No, domain wall cannot be proved by neutron scattering.
They cannot be proved. Okay.
Yeah, no. You cannot probe the main wall because it's not ordered object. But it still doesn't mean that it cannot contribute, let's say, to transport property. If you have a materials with domain walls, which are topological objects locally, they can contribute to your transport properties and give you a topological Hall effect.
I mean, if you have topological Hall effect, how do you identify whether it's from chiral domain wall or something else?
It's a challenge.
Okay.
So if you just measure your transport properties, your Hall effect, of course you have no idea that actually comes from a skyrmion lattice or it comes from something else. So you need some additional, you need scattering experiment first of all. And if scattering experiment confirms that you have some modulated crystal magnetic structures, and yes. And it satisfies, I'll show you the condition for skermion, what is a multi-case structure, and it has to satisfy some conditions. And if they are fulfilled, then you can claim probably that yes, this effect comes from the skermion.
Okay, thank you.
One more question. Okay. Let's have tea break. The topological, the problem. I believe you will give us some example, right? Yeah. Okay.
Does it work? Yeah. Yeah, I'll give you an example later on. So first I want to give you some tools, discuss some coupling phenomena, and that will probably, I hope it will help you in future to understand and to distinguish, one case structure from multi-case structure, which is very hard experimental. And to do that, we need a little bit theory. So we stopped at the fact that we want to describe, using crystallographic methods, we want to describe skermion lattice. We want to see how does it look if we try to describe, if we want to describe it within the framework of Landau theory. And in the Landau, at the core of Landau theory is a decomposition of what Landau called density function. It's something what breaks this image. So basically it's distortions. And at the core of the theory is decomposition of these distortions into set of symmetry adapted distortion modes transformed as basis functions of irreducible representations of the paramagnetic or parent, let's say parent space group, because we are talking about distortion in a very general way. So this distortion can be anything, whatever you want. It can be magnetic moment, it can be atomic displacement or some cation ordering. It doesn't matter. So that is a basic postulate, if you want, of the Landau theory. So he formulated his theory. It's more than 100 years ago already. Or maybe not. It was probably 1936. So, and the language of representation theory and the language of a group theory. So, and this sum, you see, I mean, the sum, we have a sum over S, so it goes through all the reducible representations. And F, if representation is multidimensional, then F indexes numerate basis function for multidimensional errors. So this is absolutely rigorous expression. It must be like that. It's not an approximation of it. It comes from the properties of irreducible representations. For our discussion, what is essential, and Manuel already mentioned it about that, so we need to define, so order parameter, it has been defined at several points before, several lectures before me, Brenton, Ruan, Manuel, they all define it already, so you should have an idea what this order parameter is. So it's just this coefficient, eta, in the decomposition. So basically, they tell which kind of distortion mode, which kind of basis functions we have to combine in order to describe our distorted child using language of Brenton structure. So we have a parent structure with unbroken symmetry, and we have a dissymmetric in the language of Landau theory or child structure where symmetry is broken. So the order parameter component, this eta 1, eta 2, basically it's a vector in the representation space. And it just simply tells what mixing coefficient between basis functions. It tells which distortions, because basis functions is distortion. We have to combine in order to describe our dissymmetric phase. So we have to distinguish primary order parameter and secondary order parameter. So the primary order parameter, it's a set of these parameters which fully defines the symmetry of the disymmetric or child phase. And Manuel already mentioned about that. And by the way, this condition of a single reducible representation for continuous phase transitions in the Landau framework of Landau theory, it applies to primary order parameter. The primary order parameter has to be irreducible. But on top of that, we can have, this decomposition, general decomposition of the density function can contain some other distortions. They're called secondary order parameters. So they're simply allowed to be there. So what does mean symmetry permits something? What does mean that they're allowed? It means that if we add this distortion, symmetry doesn't change. That's what it means, symmetry. But if we consider them separately, the secondary order parameter, they will have a symmetry higher than the primary order parameter. So they don't break our symmetry down to the level as low as primary order parameter. But they allow it. As soon as symmetry is broken by primary order parameter, then the presence of secondary order parameter is allowed. And as it has been explained by Rohan Carvajal very nicely in his lecture, so basis functions of irreducible representation are block functions. So which are just a product of some periodic function U. That's what you calculate, basically. So it's a localized atomic basis function. That's what you calculate when you're dealing with a magnetic ordering and you're trying to apply representation analysis. That's what you calculate. You calculate this periodic functions, that localized atomic basis function. It's a product of U and some phase factor. And again, as has been explained in a very plain way, that this form, we have this complex exponent because we have each space group has a subgroup of translations. And translations are commutative groups and a group of translations. And all representations are one-dimensional. And this complex numbers are representations of basically our group of translations. And propagation vector enumerates different representations. So it's a block functions. And now if we have a look at our decomposition, we see that our Landau decomposition is just simply decomposition of our distortions into Fourier series of the component which in general case are associated with the Fourier components associated with different propagation vector. That's what it is. And it's very natural because we are dealing with periodic structures and that they can be decomposed into Fourier series. And when I just want to mention, it has been shown many times during this school that when that all reducible representation matrices, they have been tabulated. And there are very nice tools on Bilbao Crystallographic theory and isotropy software. So I personally use always these two tools in order to generate in my calculation matrix of irreducible representation. Okay, so just to refresh your memory, again, it has been explained many times, but it's essential for our talk. So just a few words about Weif-Vector group and Weif-Vector star. So if we take our basis functions, any arbitrary basis functions, our block function, and we apply one symmetry element of paramagnetic space group, or let's say parent space group, beta, which contained some translation and some point symmetry element. If we apply it for our basis functions, then basically translation simply changes, gives us a phase factor, which is very natural. Translation simply we translate and we change our modulation of our modulated functions. While a point symmetry element will transform this Fourier component into another one, and with propagation vector k prime. And here we can have two situations. Either this k prime is identical to the k, so it acts as this point symmetry element acts on a propagation vector in the same way as a no polar vector. So, and we can have a situation when it doesn't change or changes to equivalent one, so that up to reciprocal translation. Or another situation that symmetry element will generate another non-equivalent propagation vector. So non-equivalent, it means that there is no reciprocal translation which connect k initial propagation vector and k prime after the transformation one. Then in this case, we tell that this symmetry element generates a new arm of the wave vector star. And if we go through all symmetry elements of our parent structures, and we can, those symmetry elements which don't change propagation vector or change it to equivalent one, they will constitute wave vector group. They will be part of the wave vector group, while the rest symmetry elements will create a wave vector star, okay, a set of propagation, non-equivalent propagation vectors. They're symmetry related, but they're non-equivalent in the sense that there is no reciprocal translation which connects them. So what does it mean again if we back to our initial decomposition? It implies that in a general case of distortions, our distortions are decomposed into Fourier components which are associated with different arms of the star. So we can have multi-K structure. And again, it's not so multi-K is not only about magnetism, you know, any distortion, structural distortion can be multi-K as well. So this decomposition shows that in general case we can have several arms or full star in the decomposition of these distortions. Okay, and talking about magnetism, so that was a very general distortion, but talking about magnetism, nothing special, basically. It's also our distortions, you know. And in this case, our density functions just localize magnetic moments. They can be decomposed to Fourier series as this method of refinement magnetic structure has been implemented into full proof, and it's personally my always first choice. I love this method. I find it's very physical, and because of this reason, because it is very direct connection with Landau's theory. And in the language of full proof, this Fourier coefficient, that is basically our function u in the block function. What they just in the case of magnetic, we call them S. So it can be a complex vector. Again, nothing complicated here. This complex vector simply define our plane of spin rotation, because when it's real, when Fourier coefficient is real, it's a spin density wave. So spin doesn't rotate when we propagate through the crystal. But when it's complex, we have a real and imaginary component which define our spin of plane of spin rotation. So spin starts rotating in this plane. So this is a very easy concept, and we can distinguish two cases of helical and cycloidal structure. So helical is one real and imaginary components are both perpendicular to the propagation vector, and cycloid when one of them along the propagation vector. In the case of low symmetry magnetic structure, we can have admixture. We can have a admixture of helical and cycloidal component. So what is essential? Again, it has been explained for you already, but I want to stress it because it's important for the rest of the talk, that magnetic moment or any other distortions, it's a real physical quantity. And this necessarily, what does it mean? It means that we necessarily should have Fourier component associated with plus k and minus k. So if we do our scattering experiment, we always have fundamental peak and satellite, which correspond to k and minus k. We cannot have a situation when we have a satellite only which correspond either to k or minus k. There has to be always two components, because that's what make the moment real. And in the case of complex Fourier components for Fourier coefficients, we have this relationship that they have to be complex conjugate to each other. In this case, this expression will always be real. That's what essential for us. Moment is real. We have always k and minus k component. So it means Yeah, it means that in a general case, right? So when we are talking about, let's say, multi-K structure, so we should always have at least K and minus K. It's already, in theory, it's already multi-K. But usually the term like multi-K structure is applied when we have at least two pairs of K and minus K. So K and minus K still considered as a single K structure. But multi-K structure, when we have more than one K and minus K. And multi-K structure in general case, again, does not imply that it has to be a component of same star. But implicitly, usually, if you see in the title of a paper, multi-K, it's implied that that people are talking about different arms of the same star. That is a multi-K structure. Okay? So, and this slide just, but it has been shown again very nicely in tutorials that you can describe magnetic structure using this formalism of Fourier decomposition of your magnetic structure as a Fourier series. As I said, this is my primary choice when I do refinement of magnetic structures. But I'm not going to stay here on that stuff. So what is all about? What I want to say, why I was trying to repeat all this stuff again and again for you about this business of effector star. And so, because this Skermion lattice is an example of multi-K structure. That's what it is. So this complicated ground state, which looks like that, that is the case of a 3K structure. So they have to satisfy some conditions. For instance, in the classical MNSI, the first condition is 3 ellipses, 3 helical components. So it means that the real and imaginary component are perpendicular to the propagation vector. Second, it has to be 3 arms. 3 again implies, if you take into account K and minus K, will be 6 arms. You see, that's why in the diffraction, what we had before, when it was experimentally determined, it's a 6 spots. But it's a 3K structure. It's called 3K structure. But if you take into account K and minus K, then it will be 6. So the second condition, they have to sum to 0, this 3K. And again, there is a good reason for that. If time permits, I will explain you why it's like that. And some of the magnetic phases. So magnetic phases, when in the language of foolproof, so we have real imaginary component, 2 orthogonal vector which define our plane of spin rotation, and magnetic phases simply tells you where in between a real and imaginary component your moment is. It has to sum, so for this 3 helical component, it has to sum to 120 degrees. So that is our Skermion structure in the simplest case. So it's a multi-K structure, and it looks like that. It's quite nice, right? So that was the case MNSI. That is also the case of this gadolinium 2 palladium silica 3. So it's centrosymmetric Skermion, but it's again logic is same. So we have 3 arms of the star, and that give us this Skermion lattice. Very nice ground state. So apart from Skermion lattice, we can have something more complicated. We can have cases of ordering of Hedgehogs topological defects, so they're also topological objects, but as I said before, they looked very similar to how our Skermion after a stereographic projection on a sphere. They look like a hedgehog, actually. So in this case, in the case of hedgehog lattices, it's also multi-K structure, and we can distinguish 2 cases. So one of them is a 4K structure in tetrahedron, which sum to 0, and another case 3K structure, but this 3K, they don't sum to 0. So examples of these lattices can be found in this paper. That paper is dealing with cubic perovskite, strontium iron 3, and this data have been measured on WISH, these magnetic structures, and yes, we have seen this beautiful, with our Japanese users, we managed to figure out this beautiful magnetic structure. Okay, so generally speaking about multi-K structures and why it is challenge. I mean, if you take the simplest case, let's say tetragonal, why experimentally it's very challenging, to understand that we indeed are dealing with something multi-K. So if you take a simple tetragonal crystal and take a one modulation, let's say in plane along A direction, say A star or B star, doesn't matter, then it breaks fourfold symmetry. And as explained Manuel just previously, that we should expect domains. It follows directly from the Curie principle. We must have domains. And having domains, so in our sample, our diffraction picture will look exactly same for 1K structure like for 4K structure. Single domain 2K structure will look exactly same as a 1K structure plus domains. That's why it's a challenge experimentally to understand is it actually multi-K or 1K structure. And that's why in most cases people, of course, follow the simplest procedure and just assume that it's a 1K structure. But locally, microscopically, the structure will look very different, and it's very essential and it's very important for physical properties to understand is it multi-K structure or single K structure. And so, can we actually figure out somehow is it one or multi-K structure? Yes, we can. I mean, one of the ways, so we can apply some perturbations to the system, right? So if it's domains, and we apply, let's say, some uniaxial, so domains means that fourfold symmetry is broken, and we can apply uniaxial strain, which will be a conjugate field for orthorhombic strains in each domain. And then we can manipulate, and when we apply the strain, we can detwin our crystal. And in this case, if it's a 1K structure, one pair of satellite will just disappear. But in reality, it's easy to say, but it's very hard to do, it's very challenging to do it experimentally. Do experiment with uniaxial stress, it's very hard. So you need to think about many details. You need to understand how you need to apply your strain. You need to cut your crystal in the right way. You need to think about geometry of your experiment, what will be your scattering plane, to make sure that you won't block, let's say, scattered beam with your cell. Your cell will be massive, your crystal will be tiny. This crystal will break many times, when you apply the strain. So it's very, very challenging experiment. So this way, let's say, it's very hard way to figure out. We can apply magnetic field, hoping again that it will do the job and will depopulate our domains. But again, it's not easy. You again need to do it in the right way. And even if you apply the field and you see some changes, you never know. It's just because you induce new phase or it's just because you depopulating your domains. So this is a challenge, this is a challenge, and there is no, let's say, easy way, unfortunately, to answer the question 1K or 2K. But I want to show you some other, ticks, some other ways and details, let's say, you need to go really in details of difference in symmetry between 1K and 2K structure to understand them. But they can they can help you to figure out is it 1K or 2K structure. So we need to explore a little bit coupling phenomena in the case of 1K and multi-K structure. And coupling is always about symmetry. Coupling of secondary order distortions, secondary order parameters. And coupling is, as I said, is all about symmetry, and since 1K structure and 2K structure have distinct symmetry, so we should expect a different type of coupling in these two situations. And this coupled degrees of freedom is a distortion which can be probed with the scattering techniques. And that's what I want to show you, and that's what I want you to understand. So in order to have an idea how it works, we need to get back to the Landau theory. And in this case, we need to get back to the free energy decomposition. So it's a thermodynamical part of Landau theory, which tells that free energy free energy which is responsible for stability of our D-symmetric or child phase, can be decomposed into powers of order parameter component. So you probably have seen in literature this type of Landau decomposition, right? When you have quadratic quartic terms. So eta our primary order parameter. So it's always, in most cases, you will see this decomposition which includes only primary order parameter, magnetization, polarization, or whatever. So each of these terms in this decomposition is invariant. It must be invariant in respect of all symmetry operations of our parent structure, because free energy, it's energy, it's a scalar quantity. Scalar is invariant under all symmetry operations. But the decomposition, so in this example, what I tell, eta is a primary order parameter. That's one which breaks the symmetry. But the decomposition also can contain some terms, coupling terms. That's what the coupling start to be a player. So we can include some terms, some invariant, free energy invariant, which can combine components of secondary and primary order parameters. And this coupling terms, they also must be invariant in respect of all symmetry operations of our group. And you see in this example, so I'm using eta. It stands for primary order parameter, so POP means primary order parameter. So it's transformed by some irreducible representation, which can be only one in the case of continuous order phase transition, for instance. And the associated order parameter, as we discussed above, will always contain component eta and eta star, where eta star is complex conjugate. As we saw before, our magnetic structure has to always combine K minus K and complex conjugate in a general case. So that is a primary order parameter. So propagation vector, so modulation. We are talking now about modulated crystal structure, because, for instance, in most cases, if you are dealing with topological structures like Schermion lattices, it will be modulation. It will be incommensurate modulation. And secondary order parameter here is the delta. And it's again, so SOP, it's a secondary order parameter. It transforms by some other representation. So far I don't specify which of them, doesn't matter. It will be some representation which will transform them. And we have an order parameter component associated again with delta and delta star. So K minus K, complex and complex conjugate. And the modulation is KSOP. So it's a propagation vector of secondary order parameter. That's what it is. So what I am trying to achieve, why I need all these terms and free energy, I'm trying to answer the question, what kind of distortion we should expect if we have a modulated crystal structure with a propagation vector, let's say KPOP, primary order parameter. What else shall we expect in the case in our structure? So from experimentalist point of view, I'm interested in two things. First, is it secondary distortions are magnetic or non-magnetic? So if it's magnetic, it means it's time odd. So they change time, they change sign under time reversal symmetry. Or non-magnetic, time even. The first thing what I want to know, because if I'm going to on synchrotron bin line, and I want to play with polarization, sigma, sigma pi, and so on, to see in which channel I should see the signal, I need to know is it magnetic or non-magnetic. And second, what will be the propagation vector for the secondary distortion? So I know my propagation vector for primary order parameter. Let's say as we have seen on the previous slide, we have this 4 spots. Let's say I know that from diffraction experiment. What else will be there, and what else will be what will be the propagation vector of the secondary order parameter components? That's what I'm trying to answer. And if we include this invariant, so it has to look something like that. You know, I don't know explicitly the form, but it has to look something like that. The rule is that if something is allowed by symmetry, it will necessarily form the free energy coupling invariant linear in respect of this physical quantity, in respect of the component of the secondary order parameter. That is the rule. It must be like that. And that means in respect of the primary order parameter component, this invariant can be any, you know, some n power of the, n cannot be 1, because if it's n equals 1, that we have simply bilinear coupling, and that is possible only if delta and eta transform by same irreducible representation. But by definition, by default, we are looking for on scattering or something secondary order parameter. So n cannot be 1. So secondary order parameter distinct from the primary one. That n can be 2, 3, and so on. And it has to look something like that. And if we take into account our k and minus k complex, a complex conjugate component, that will transform in this form. That will be combination of complex and complex conjugate components from both sides, secondary order parameter, primary order parameter, with appropriate power of the primary order parameter. That kind of, it's sufficient. It's already for me sufficient to know that in order to do very general conclusions. And yeah, I'll show you in the next slide what all this means. And another interesting thing, what I want to bring your attention, that if now we include this coupling term, we can also include invariant quadratic in respect of the secondary order parameter. Because quadratic invariant is always allowed. It's a trivial, it's called trivial invariant. It always will be in the free energy decomposition. And if now I will minimize my free energy, I will find out that if something is allowed by symmetry, if this invariant indeed is allowed by symmetry, then it will, equilibrium condition requires that it will necessarily be non-zero. That is the answer on the question. You know, many times we had here a situation where symmetry allows something, you know, but our data are not sensitive to that. And that is the answer on the question, that this physical quantity must be non-zero, because that is requirement of the equilibrium condition. Only in this case, free energy is minimized. So it's accidentally, it's in other words, we can formulate the rule, you know, physical quantity is zero only if it's a requirement of the symmetry. So if symmetry doesn't require something to be zero, we always have this invariant, coupling invariant in free energy, and this coupling invariant will give us non-zero finite value. It can be very small, so our data can be not, but it will be finite. So it will be there. That is essential to understand that. Okay, so so let's back to our question. So what we want to figure out, what we want to answer. So we have a primary distortion, modulated crystal structure. We know it from experiment. It will be very easy to figure out using scattering techniques, your primary modulation. So what else shall we expect in our structure, in the case of 1K structure and multi-K structure? What other distortions, what they are, magnetic or non-magnetic, time odd or even, and what is their modulation? That's what we want to answer. In order to answer this question, we need just two symmetries. We just need translation symmetry, and we just need time reversal symmetry, nothing else. And translation symmetry, it's always looked like that. It's simply in any reducible representation, it's just a diagonal matrix, which contains phase factors, you know, for k and minus k component of order parameter. So it just acts in the space of order parameter. It's like any operator, you know, acts in some function. And time reversal has a even simpler form. You know, it's diagonal and just contain -1. So it just swap sign for each. If this order parameter is magnetic, then it will swap it. If it's non-magnetic, then it will be simply diagonal matrix, unit matrix, and it will keep it. No, there will be, yes. So I'm just explaining how it works. Here, let's first consider the case that we have only one propagation vector. So our eta1, eta star is just a multidimensional array, and with one, so far, with only one modulation vector. Let's assume like that. what shall we expect in this case? It's a 1K structure. It's useful to know what we should expect. So if now we apply these two symmetry operators on our order parameter, and we take on our invariant, so we are checking, do we have this invariant? Can we have this invariant or not? And what we need to do in order to make this expression to be invariant in respect of our symmetry element, our translation. So translation will simply introduce this, what is shown in red, our phase factors, That's what it will do for a primary order parameter. That's what it will do for secondary order parameter. For secondary, primary, secondary, primary. And now we need to make sure that all this expression is invariant. So basically this product of this phase factor has to be 1. Because before transformation and after transformation, this coupling term should look exactly the same. And that imposes a condition for the modulation of our secondary distortion. So it simply means that our sum of the secondary order parameter, propagation vector of the secondary order parameter, and n times propagation vector of the primary order parameter, n is the power of our invariant, equals to 0. In the simplest case to 0, more generally, it has to just go to reciprocal translation. Has to be, so it's called propagation vector conservation law. But for simplicity, let's consider just 0. So that means that our propagation vector, secondary order parameter, must be just a product of n, k, primary order parameter. So it's nothing else as our harmonics. That's what it is. So in the case of one modulation, we should expect harmonics. And the secondary condition of time reversal, so in order to this free energy term be invariant in respect of the time reversal, we need to see on the power of this invariant. So it will be invariant if all components which are time odd, they are even. So for instance, if our magnetic order parameter, primary magnetic order parameter is magnetic, so is time odd, then if we take n is an odd number, then it implies that delta, our secondary order parameter, must be also time odd in order to keep even power for the entire invariant. And opposite, if n is even number, then delta can be even as well, can be structural distortion. That gives us famous condition, So n even, delta, our secondary, our harmonic, is time even. It's a structural order parameter. If n is odd, delta is time odd. It's a magnetic harmonic. Probably some of you at least know that in the case of modulated structure, we should expect harmonics. But now you know why. That comes from this general, it's very general, do you see? I mean, I didn't specify, I didn't assume any magnetic symmetry, any magnetic space group, or even the representation. It just comes from the very general concentration of the Landau free energy. So it's another way how you can work with symmetry in a very general way. So it's a Landau free energy decomposition. Okay? And now let's see what we should expect, what kind of secondary distortion we should expect in the case of multiple arms. If you have if several arms of the star are involved. So in this case, so our invariance, it will contain the so our eta s star. So it's a k minus k component for one arm, and nf star. It's a component, k minus k component, complex conjugate components for another arm of the star. So they are associated with this k minus k primary order parameter. So, and now we have a primary order parameter ks, so one arm, a kf, another arm of the star. So our free energy invariant will look something like that. So again, it will look much more complicated, but it will be these terms. In this invariant, there will be these terms which will couple secondary order parameter with different arms of the star involved in the transition. And that's what we are interested in. they will do the job what we want. So again, if we apply a translation, we are checking two symmetries: translational symmetry, time reversal symmetry. Then we will get these phase factors, and requirement of invariance will tell us that we should expect secondary order parameter distortions, which are combinations of our arms. So in the simplest case, if we have a transition, if we have magnetic structure, multi-K magnetic structure, where we have K1 and K2, let's say that is our Ks and Kf, we should expect structural distortions with propagation vector Ks plus Kf, K1 plus K2. This structural, so this propagation vector, so it's, as I said, it's a structural distortion. We can probe it with a scattering technique. We can go to synchrotron and we can measure. Now we know where in the reciprocal space we need to look at, where we need to, and if we see this reflection, so they're not, so there will be harmonics as well for each arm, but on top of that, on top of the harmonic, we will have this structural distortion with the combinations of this arm of the star, and we can check. I mean, we can check it. And what happens if we apply the magnetic field? If we apply the magnetic field component, so it's a translational invariant, it's a K0, and it's time odd quantity, it's a magnetic. So it's change sign and the time reversal. So in this case, if we include this component of the field in our free energy decomposition, we should expect that in this case, K1 plus K2 will also contain magnetic contribution. So if we have 2K magnetic structure and we apply magnetic field, then on top of the structural distortion, which will be very hard to see with neutron diffractions because they are very weak, we will have also magnetic contribution to the K1 plus K2, coming from this coupling term, which combines also a magnetic field. Okay? You can see, I mean, because some people use these tricks and, to justify the multi-K structure. But now you at least have an idea from where this logic comes from, why you need to do that, and why it indicates that it's an evidence, indeed, an evidence of multi-K magnetic structure. And then on top of that, we will have some other higher order, I don't know, call them harmonics, probably not strictly speaking harmonics. It will be higher order modulations, let's say, which will combine components of primary order parameters. Some of them will be linear, some of them will be in some power. So in the simplest case, again, if n equals 2, let's say, then we will have, if we have K1, K2, then we should expect magnetic modulation with propagation vector K1 plus 2K, 2K2, or 2K1 plus K2. So there will be magnetic contribution with this modulation. Okay, it's again we can check it using if you have a good quality crystal, if you have a good quality instrument, we can check all that stuff. So I guess it's time to show you how it works. Yeah. In real data. I will show you some skyrmion crystal, and we show, okay, we have some time. So just before I start showing the actual, explicitly how it works, all that theory and all that stuff on real data, let me just mention another trick which can help you as well to figure out are you dealing with single or multi-K magnetic structures. So as we discussed above, right, so and you already know, so it has been repeated many times here that arms of the star is just symmetry-related component of symmetry-related Fourier components. And but what happens with paramagnetic? They're related by symmetry element of the paramagnetic space group. But what happens if our magnetic structure allows this, let's say, kills the symmetry element which interchange propagation vectors. So they are not symmetry related anymore in the magnetically ordered state. And that means that, strictly speaking, there is no condition that these arms has to be exactly same, at least their length. And that can give you another clue, you know, another indicator that you are dealing with multi-K structure. Because in this case, your propagation vector will be slightly different. You know, this information explicitly and very clear can appears in the superspace group formalism. So it's very naturally, you know, I took just a simple cubic space group with 3 modulation vectors. You see this along a direction. And I ask IsoDistort to generate for me superspace groups for that case. And it's generated for me 3 space groups. And in the first one, when magnetic superspace group is cubic, so there are symmetry elements which interchange arms of the star. That implies that all 3 arms, all three modulations in the superspace group must be the same. So you see it's A along A along B, A along C. But in the next one, the magnetic superspace group is tetragonal. And in this case, modulation in plane, yes, has to be same, A1, 0, and 0, A1, but along the C-axis can be different. So that means that there is no symmetry constraint why the third modulation that along the C-axis be the same as in plane one. And if there is no the symmetry requirement, as we discussed about, they will be necessarily different. And if your resolution is good enough, you will see it. And I'll show you in the real data that is really the case. Okay, that is another, let's say, information what you need to keep in mind if you want to understand are you dealing with single K or multi-K structures. Okay, and now let me show you how much time I have. 15 minutes. So I'll show you how it works in some examples. So let's take this gadolinium ruthenium-2 silica-2. This is central symmetric skyrmion host, which was very recently discovered, and people are very excited about that. But again, skyrmion phase here in the phase diagram, you know, it appears in field. But in our study, on which we were first interested in the ground state, because in order to understand what interactions stabilize skyrmion phase in applied field, we need to understand the ground state first in that material. And that is the example, that's a cut of reciprocal plane measured on WISH for this crystal. So it's gadolinium, but it was isotopically substituted. So it was a huge crystal and scattered very well. So what we see fundamental peak at the position, so it's HK at the position -1, 1. And we see 4 satellites. K1 minus K1, K2 plus K2 minus K2. So the question is, again, is it multi-K or 1K structure? And on top of that, you know, if you optimize your geometry and if you optimize your scattering condition, like for that, we did it for superposition K1 and K2, you know, we found this peak is here. That's what tells us that, yes, this probably 2K structure. And on top of that, again, if you optimize the condition, you can see higher order satellites. You see 2K1 plus K2, K1 plus 2K2, and so on and so on. So you don't see him here and here because, again, at that position, you know, it was optimized for flux was only this one, this satellite. We cannot at the same time, you know, measure with very high precision all of them. We need to rotate the crystal. And that of course takes time, and on which if you get 1 day, you're already lucky. So you can do only essential measurements. And you need to optimize just minimum to get information what you need from a minimum number of set of measurements. So you see, we have all that stuff what I was talking about. So we have K1 plus K2, we have, which has to be structural, K1 plus 2K2, which has to be magnetic. From this data, we cannot conclude is it magnetic or not. But then this crystal was also studied at Diamond on I-16. It's a resonance X-ray scattering diffraction, where playing with polarization with sigma pi sigma sigma, you can decide is it magnetic or it's structural. And it has been done, and indeed this K1 plus K2, it's a structural, and K1 plus 2K2, it's a magnetic, exactly like it should be. So based on that information, we concluded that the ground state of this fermion host is a multi-K structure. But on top of that, so the interesting thing is so it's not clear here because resolution is not good, but if we optimize again scattering condition and we look at the spots here, we see that they're split. You see? So we have two propagation vectors, and these two propagation vectors are not equivalent to each other. So we have two K structure, but we still have these arms, they are not equivalent. And they're different, and they're different. You just need a resolution in order to see that. And based on all that information, so why it's split? Because we have domains. So since they are not equivalent, that means that four-fold symmetry is lost, and these arms no more required to be same, and they are different, and on top of that we will also have domain. So we just on one shot, on one spot, yeah, we have a superposition of two domains. That's why we see two peaks. And this domains has K vectors which are slightly different. Okay, and having this information, we managed to solve the magnetic structure, which is very nice, actually. So it's a combination of, in order to get constant moment, but constant moment in this material usually is always physical solution because, you know, F electrons are localized. And in order to avoid residual entropy associated with disordered spin, usually you always try to find constant moment solution as a ground state. And this solution actually includes two helical components. So one of them is K1, it's our, let's say, fundamental component, the primary order parameter component. And we have another helical component, K1 plus 2, K2. And we have another component, K2, it's a spin density wave. So you see our 2K structure involves two arms of the star, but one of them is spin density wave, another is helix. That's why they're different. You know, they cannot be symmetry element which interchange helix with spin density wave. So they're different. There's two arms, but they're different. And since this component, spin density and helical component are different, there is no requirement why the propagation vector has to be same, in spite of the fact that they're same arm of the same star. And on top of that, in order to get a constant moment solution, we just need to add another helical component, that is K1 plus K2, which we have seen experimentally with this condition of for the amplitude. And yes, it fits the data. So we feed the powder data as well using this model. It fits very well. And you see on the powder data with very good resolution, you can see the splitting of the reflection. That is our splitting of our K1 and K2. Okay. That's how it works. So that's what you need to keep in mind when you deal with, and you suspect that you can have a multi-K structure. Usually it is the case when you deal with high symmetry crystals, you know, it's cubic, tetragonal, hexagonal, etc. Okay, and finally, before finishing, I'll show you another example, you know, very nice example, because we have a few minutes. Where again, using this logic, what I was talking about above, helps to sort out very, very complicated magnetic structure. It's a ground state in neodymium boron 2. So I was shown, you know, some of our users showed me this data, which were collected on G7 at ILL. So it's a polarized neutrons data. It's in spin flip channel. So it's, as you know, after Javier talk, so there has to go a magnetic contribution on. And when I've seen that first time, this picture, I was really puzzled because we have a modulation. You have a modulation close to 1/5, 0, 2/5. And on top of that, we have a second harmonic as well. And this harmonic is very strong. And I ask, did you measure this crystalline field? Because second harmonic has to be non-magnetic, as we discussed above. It's requirement, but very fundamental symmetry, you know. and it should not be here. But that's a spin flip channel. It's magnetic. Only magnetic scattering can go here. And he said, no, it's in zero field. And I was really puzzled how it's possible. And then I noted that we have also K0 component here. That actually made the situation clear. That solved the puzzle. Because why we need a magnetic field in order to have second harmonic? Because magnetic field is translationally invariant, and it's magnetic, it's time odd. Exactly same role in our free energy invariant can be taken by some other K0 component, and it doesn't need to be ferromagnetic. It's only need to be magnetic, time odd, and it's only need to be translationally symmetric, K0. And we have this component here. And this component is actually antiferromagnetic, and it works like internal staggered field. You know, and the magnetic ground state is actually very funny. So that when I understood that stuff, I managed to sort out very quickly this magnetic structure. So it's very nice. It's a case where we have alternation of 3 spin up, 2 spin down in respect of the internal field. So 3 up, so internal field, our K0 antiferromagnetic component alternate in the crystal, up, down, up, down. And our modulated component does exactly the same. So it produces spins along the internal field. It's 3 up, 2 down, and then opposite, 3 down, 2 up, and like that, alternate like that. That's what gives this, so it's anharmonic spin density wave, and that's why our second harmonic is huge. It's very big. But again, this logic, what I told you, helped me to sort it out, this extremely complex case. Okay, I think we can just make some very brief conclusions. So the basic idea of topology, as I hope I managed to show you, provides some understanding of stability of some defects or excitation in magnetic materials. So I hope you understood how these simple ideas actually can help to understand why these skermions, for instance, why they can exist as isolated objects, because they're very stable, you know. If they create it, if you find a way how to inject them in your system, then it's very hard to get rid of them. And topologically non-trivial magnetic textures represent examples of multi-case structure. So when we have a case of long-range order topological defects, that on our language of crystallographer implies that we have multi-K magnetic structures. And finally, couple secondary distortion harmonics carry information about multi-K nature of magnetic structure. That is the key how we can understand that we indeed are dealing with multi-K structures. And again, not all of them, if multi-K structure does not mean necessarily that it will be topological, you know, and it will be skermion lattice. But at least this will be, it's a necessary condition. So you need, again, in order to verify that you need either quantitative refinement, you need some other, like transport measurements to check the topological Hall effect, and so on and so on. And all together, all this information together can help you to make a decision whether you are dealing with skermion lattice or topological or some other topological multi-case structure. Okay, thank you.
Thank you, speaker. We have a couple minutes. Can have few questions.
Thank you for your nice talk. I have one question. I think it seems sometimes it would be very complicated to discriminate the magnetic structure with multi-Q from the multi-domain, so such as in the honeycomb lattice cobalt, because someone claimed that it would be a triple Q magnetic structure, but very recently there's also report that it would be multi-domain magnetic structure. So what's the key difference, or is there any good solution for us to discriminate one from the other? Yeah.
So you're talking about triple Q in honeycomb lattice.
Yeah. Or some else, some other compound. Maybe it looks like a multi-domain could give similar.
Yes, of course. Multi-domain will give you similar. That's what I mentioned, that based on just that information, you cannot decide is it multi-K or, so you need additional details of your magnetic structure, and one of them, you need to look at the right reciprocal point, of your reciprocal lattice, and that one, K1 plus K2, for instance, or K1 plus 2K2,
Yeah.
that is a key. So if these reflections are there, then it's a multi-K structure. If these reflections are not there, then it's probably 1K structure.
I see. Okay, thank you very much.
Yes, I mean, we have recently done some experiment also. I mean, you still can use your traditional, let's say, uniaxial strain, let's say, or application of magnetic field, and we recently completed successfully for our Chinese users one of this Kitaev system for 3K case. And we just, in order to distinguish and confirm that it's 3K structure, we applied, in this case, uniaxial strain. But these guys are very good, and they know what they are doing. They came very prepared, all cell was set up, and the experiment worked beautifully. But it's extremely complex. These experiments are very complex. And another way, as I said, in my opinion, it's simpler. You just need to look at with the right technique, synchrotron perhaps, right at the right point of the reciprocal lattice to check, do you have this high order satellite or not.
Okay, thank you. Thank you very much.
One comment that I see that you have not followed the recommendation that you said the other day that you should submit your structures to the database, because I check and these two very nice structures, they are not there.
I apologize. First of all, Manuel, we still haven't figured out magnetic superspace group for this state. I refine the structure using Fourier decomposition because, again, it's my primary choice, and it's very physical, as I said. When I understand the physics, and I can, I can parameterize and I can decompose the structure. But yes, we will do it because I'm curious as well. Because as I said, superspace group should not interchange these arms, and I want to see it explicit. So I just need to sit down and work out superspace group and transfer this refinement to MShift and upload. Yes, I'll do it.
But, what about the commensurate one? Because the commensurate one, there are, for the same compound, other entries.
Yes, the commensurate one I can, yeah. I even supplied MShift, I think, for yeah, this I should do it, yes. I have MShift for that, and again, it was refined as a Fourier decomposition. Because you see, I mean, that is advantage. In this case, magnetic symmetry is monoclinic with probably something like 5 independent atoms. So each atom has 3 components. But using Fourier decomposition, I refined this structure using only 2 parameters. And refinement was very good. So, but yes, I worked out MC file and the symmetry for that, and yeah, I will submit.
And you mentioned when you talked about secondary order parameters,
yes,
you discarded secondary order parameters of the same rep. But in fact, they could exist, and they exist in general, at least for structural order parameters. That means they are not quadratically
no, they will be quadratic. Yes, yes, yes.
They are not quadratic because you are already assuming they are normal order parameters.
Yes, I mean, I'm talking here about bisymmetry. Bisymmetry, they will be still prime. Like for instance, weak ferromagnet. Yes, it is a secondary order parameter, but bisymmetry, same rep, but it has exactly the same symmetry as the primary one. And yes, but I agree with your comment. You can have this
these are
type
the
of
degrees of freedom which have the same symmetry. As
yes. But in this case, you see, in the context of my talks, they are quite trivial. They won't give you any additional information. We need to see something different from that, which will confirm that it's a multi-K structure.
One more question.
Hi, for the gadolinium ruthenium 2 silicon 2, You showed there's so the K1 plus 2 K2 is harmonic, right?
Yes.
But in the final refinement of the crystal structure, you include like the all the harmonic and the basic, right?
Yes, I
So why
included.
I think so. You said that this harmonic is always there, but why you should include in the?
Now, what do you mean? They're always there. You mean if you're dealing with 1K structure?
For example,
Yes, I mean, if you're dealing with 1K structure, yes, you will have harmonics as well, but usually they're very small. So I just didn't mention, because that is absolutely symmetry general, consideration. We didn't take care about any microscopic reason why this distortion, secondary distortion, have to be there. But actually, it's a good point, But everything what is, as I said, everything what is allowed by things, there will be always microscopic interaction which will make them finite. And in this case of, let's say, harmonics, it will be magnetoelastic coupling. And for magnetic higher order harmonic, third harmonic, fifth harmonic, and so on, it will be anisotropy. You see, I mean, if you have a single ion anisotropy and imagine you have a cycloidal state, let's say our easy axis is vertical, and we have a cycloidal phase which includes this easy axis. So your spins, when you propagate through the crystal, it will rotate slower when you approach to the easy axis direction, and then faster when you deviate from it, because it wants to be your spins wants to be along the easy direction, and that gives you unharmonicity, and this unharmonicity will be your contribution to this odd harmonics. That's what microscopic.
My point is, so basically you also have K1 plus 4K K2, right? In principle, for the magnetic.
No, if it's only
it's
one modulation,
to
it will collapse to third harmonic. So that's what we have: K1 plus 2 K2. It will collapse to a third harmonics for one modulation. But if it's a different arms of the star, it will scatter in a completely different reciprocal point. You will not mix them up. You will not mix them up with the third harmonics, let's say, of one arm. It will be scattered and it will be completely different reciprocal point.
Yeah.
Yeah.
Okay, maybe I can talk with you later. Yeah.
Because of time concern, we speak again, and we move to the next.
Okay, thank you everyone.
The next